In 2019, global media outlets reported a groundbreaking event in astronomy. Scientists had captured the first photograph of a black hole. This image, showing a red gas sphere with a dark circular outline in the center, was seen by billions of people. The black hole captured in this image sparked immense public interest and became the leading news story worldwide for a while. This interest was driven not only by the scientific significance of black holes, but also by their presence in popular culture, including documentaries and movies. The photographed black hole, located in the M87 galaxy 53 million light-years from Earth, was captured by the Event Horizon telescope. It has a mass 6 billion times that of the Sun, and its silhouette could encompass our entire solar system, including Pluto. To capture this unique image, astronomers created a powerful super telescope. Regular radio telescopes couldn't pick up the faint signal from such a distant object, so scientists combined data from 5 different telescopes around the world and used supercomputers to precisely synchronize their signals. The resulting gigantic radio telescope, as large as our planet, could spot an orange on the surface of the Moon. These and other significant astronomical discoveries have revived interest in Einstein's theory of gravity, which had seen waning interest over the last 50 years. The equations of the general theory of relativity were extremely complex, and gravity experiments were costly, requiring sensors kilometers in size. Ironically, although Einstein himself was skeptical of quantum theory, the current resurgence in relativity theory research happened due to the merging of quantum theory and the general theory of relativity. Applying quantum theory to astronomical objects, even without considering gravitational corrections, has led to a series of breakthrough scientific discoveries. There is another theory that has seen ups and downs over the past 50 years. This theory can unite quantum mechanics, which studies the world of elementary particles, and Einstein's theory, which describes black holes, the Big Bang, and the expansion of the universe. This concept talks about the preservation of information even in the presence of black holes. Today we'll discuss string theory and its incredible evolution from a single formula to a discipline whose research works fill an entire library. String theory is now the basis for many new research projects in leading laboratories worldwide. This video continues the previous one on the theory of everything, and the information is also based on ideas from Michio Kaku's book The God Equation: The Quest for a Theory of Everything. Michio, a well-known American theoretical physicist, has been working on string theory since 1968 and provides a balanced and objective analysis of string theory, its breakthrough discoveries and shortcomings in this book. In this video, you'll learn why the search for a theory of everything has captivated the imaginations of the world's most influential scientists, and why string theory generates such passion and controversy. At the end of the video, we'll touch on the topic of searching for the meaning of the universe, its beginning, and learn what God Albert Einstein believed in. In our quest to understand the fundamental structure of the universe, we humans have historically created concepts to interpret and comprehend our world. These concepts undergo rigorous testing through the scientific method, allowing us to determine what is valuable and what can be relegated to the scrap heap of history. As our knowledge expands, some concepts become increasingly complex and sometimes even confusing, like in the case of string theory. Often misunderstood, this theory attempts to shed light on the very essence of our universe's existence. Its validity and practicality are subjects of ongoing debate, like is it revolutionary breakthrough or mere speculation, a theory of everything or a theory of nothing. To date, quantum mechanics remains the most accurate field of human knowledge. The predictions of this theory have been verified to 11 decimal places. It studies the subatomic world. However, elementary particles are so small that standard electromagnetic waves used to observe most objects in our world are too large to interact with these particles. Attempts to observe them with higher energy waves accidentally alter them. This phenomenon, known as Heisenberg's uncertainty principle, forms the foundation of quantum physics. But there is another way to look at it. Hugh Everett's interpretation tells us that every possible event actually occurs, but in parallel universes that make up a multiverse. Thus, when we observe the position of an elementary particle, we are simply learning which of these parallel universes we are in at that moment. This multiverse concept not only expands our understanding of quantum physics, but also offers a new perspective on the reality we exist in. I plan to make a video on this topic in the near future. Let me know in the comments if you are interested. The standard model views particles as points in space, each possessing unique properties such as electric charge and mass. While not entirely precise, this approach has been incredibly effective. It forms the basis of the standard model of particle physics, providing amazingly accurate predictions. For example, it can precisely predict the properties of matter in the past right up to a fraction of a second after the Big Bang. This set of particles, accurately describing our quantum universe, consists of 36 quarks and antiquarks, 12 weakly interacting particles and antiparticles, known as leptons, and a large number of Young-Mills fields and Higgs bosons. Yes, it sounds cumbersome, I agree. The matter visible to us primarily consists of particles such as electrons, quarks, and neutrinos. These particles interact with each other, exchanging various particles to transmit forces. For instance, the electromagnetic force involves the exchange of photons. These diverse particles form the standard model, dividing them into two groups: fermions, which mainly constitute matter, and bosons, primarily responsible for interactions. However, including gravity into this system poses a massive problem, as gravity determines the large-scale behavior of the universe. Every attempt to add gravity to the standard model has left physicists unable to solve the equations. Quantum corrections related to gravity, instead of being tiny, turn out to be infinite and thus meaningless. Therefore, the standard model fails to illuminate some of the universe's secrets, such as what happened before the Big Bang and what lies inside a black hole. In Einstein's general theory of relativity, gravity is not a force transmitted by particles, but a geometric property of space-time itself. It's the mismatch between the imprecision of the quantum world and the need for absolute accuracy in describing the geometry of space-time that creates a profound conflict in our understanding of the universe. String theory was proposed in an attempt to reconcile the discrepancy. It states that elementary particles are not points, but rather forms of vibration of tiny strings. This elegant solution encompasses all fundamental forces, including gravity, electromagnetism, strong and weak nuclear interactions, proposing a unified theory of the universe. Within this theory, particles are made up of tiny one-dimensional strings, which can be either open or closed. They resemble tiny rubber bands, possess tension, and can vibrate in various modes, much like a violin string produces different harmonics. These vibrations correspond to different types of particles at the macroscopic level. Interestingly, some of these vibrating strings mimic the behavior of non-particles, such as photons, offering a new perspective on the fundamental building blocks of the universe. String theory has proposed an intriguing idea regarding gravity. Some vibrational modes correspond to gravitons, theoretically explaining gravity at the quantum level. The dynamics and interaction of these strings are critically important. Take, for example, a photon directed at a target. At the quantum level, its behavior is determined statistically, that is, through the probability of various outcomes. In the standard model, this implies summing all possible trajectories and interactions. However, string theory revolutionized this approach. Particles, now strings, trace surfaces over time, not just points with trajectories. This shift to string theory means considering all possible string configurations over time, including those in which strings split, emitting a particle, or join, absorbing a particle. What a revolutionary theory! It's only logical and inevitable that it immediately faced problems. For instance, it initially predicted only bosonic particles, like photons or gravitons, but not fermions. Another problem was the prediction of tachyons, particles with imaginary mass, and the requirement of a universe with 26 dimensions, far from the 4-dimensional spacetime we observe. To solve these problems, the theory evolved into superstring theory, which includes spinors attached to strings. This addition allows for the prediction of fermions and eliminates the tachyon problem. Superstring theory also introduces supersymmetry, suggesting a fundamental symmetry between bosons and fermions. However, this changes the dimensional requirement of the universe to 10. Michio Kaku writes, "I still remember the shock that physicists experienced when string theory suddenly postulated that we live in a 10-dimensional universe. Most physicists saw this as evidence of the theory's fallacy. When John Schwartz, one of the leading architects of string theory, encountered Richard Feynman in the Caltech elevator, Feynman often teased him, asking, 'So John, in how many dimensions are you today?' The potential solution to this phenomenon lies in the concept of compact dimensions. Our universe might be a three-dimensional slice of a larger, multi-dimensional space, or some dimensions could be compactified, rolled up on scales too small to observe, similar to how an ant perceives a multi-dimensional straw. Though it has length and thickness, for the ant, which only perceives its surface, the thickness remains unnoticed. From our perspective, some dimensions remain invisible, leading to the sensation that particles move slower than they actually do. We observe only a part of their overall motion, creating the illusion that they have mass. This observation is key to the concept of compactified extra dimensions, postulating a mechanism by which particles can have significant mass. However, testing this in particle accelerators currently exceeds our technological capabilities. But more on that later. The existence of extra dimensions would allow for a wider range of vibrational modes in string theory, leading to the emergence of a diverse array of potential particle types. There are many ways to compactify these dimensions, each leading to the creation of a separate theoretical universe with unique particle behavior. By choosing specific methods of compactification, we could align our theoretical predictions with the particles observed in the universe. Nonetheless, it remains unclear why our universe exhibits the specific types of particles of the standard model and not something else. Some theories suggest that the geometry of the universe could have changed over time, transitioning between different forms of compactification, which might mean that the laws of physics evolved and changed since the universe's inception. Thus, superstring theory is already remarkably comprehensive. At its core is supersymmetry, harmoniously unifying bosons and fermions. It is the most encompassing symmetry ever discovered in physics, allowing the unification of all known particles into a single entity. We are on the brink of the final stage in the development of string theory, understanding its fundamental physical principles. One of the main mysteries here is how to derive the entire theory from a single equation. In 1995, string theory underwent a metamorphosis, becoming M-theory. Previously, the original string theory consisted of 5 separate models of quantum gravity, each consistent and well-defined but differing in the organization of spins. The main question then was, why exactly are there 5 theories? American theoretical physicist Edward Witten provided an answer in 1995, discovering a hidden 11-dimensional theory named M-theory. It is based on membranes, similar to the surface of a sphere. It turned out that these 5 string theories were merely different mathematical interpretations of one M-theory. 2 years later, in 1997, Juan Maldacena made a groundbreaking discovery, causing a sensation in the world of physics by presenting what seemed impossible. He showed that a supersymmetric Young-Mills theory describing elementary particles in 4-dimensional space and string theory in 10 dimensions are mathematically equivalent. This discovery generated giant interest among scientists, and over 20 years, his work became the most cited in the field of high-energy physics. It illustrates 2 important qualities of string theory: symmetry and duality, which are different but interconnected. Symmetry implies the invariance of the equation when rearranging its components, while duality demonstrates the mathematical equivalence of 2 different theories. An example of duality in Maxwell's equations is the interchangeability of electric and magnetic fields. Similarly, the 5 different string theories in 10 dimensions turned out to be dual to each other, ultimately representing different aspects of a single 11-dimensional M-theory. But Maldacena went further, discovering a duality between strings in 10 dimensions and Young-Mills theory in 4 dimensions. This discovery meant the presence of deep and unexpected connections between gravitational and nuclear interactions in different dimensions. Usually, dualities occur between objects of the same dimension, but Maldacena's duality between different dimensions was unprecedented. This isn't just an academic interest, it has far-reaching implications. Previously, we believed that nuclear interactions were best described by the four-dimensional Young-Mills gauge theory, but now, considering the duality with 10-dimensional string theory, the key to understanding nuclear interactions might lie in quantum gravity theory. In other words, the fundamental properties of nuclear interactions, like the mass of the proton, might be best explained through the lens of string theory. Although string theory demonstrates clear theoretical successes, beauty, and symmetry, its ambitious claims and conclusions naturally attract the attention of a whole army of critics. This reminds me of Carl Sagan's words that extraordinary claims require extraordinary evidence. Wolfgang Pauli's words also come to mind. He is known for his ability to sharply criticize, such as saying, "What you just told me was so confusing that one could not tell whether it was nonsense or not." He also liked to say, "I don't mind that you think slowly, but I do mind that you are publishing faster than you think." In debates about string theory, physicists have split into two camps, just like it was at the Sixth Congress in 1930, where Einstein and Bohr argued about quantum theory. This was the topic of my previous video on the theory of everything. Nobel laureates have also taken polar positions. Sheldon Glashow criticized the lack of testable predictions in string theory, and Gerard T. Hooft compared the attention to the theory to the hype around American TV shows.
Set.
Meanwhile, other scientists like David Gross highly rated the theory, noting that Einstein would have liked its geometric principle. And Steven Weinberg compared the development of string theory to searching for the North Pole. Glashow, a critic of string theory, acknowledged in this debate that he is in the minority, comparing himself to a dinosaur among upstart mammals. The main arguments against string theory are based on the notion that it's just a hype, that symmetry is not a reliable indicator in physics, that theory suggests the existence of too many universes, and most importantly, it cannot be experimentally verified. Various examples can be cited here. Paul Dirac asserted that scientific work should strive for mathematical beauty, and even discovered his famous electron theory not by delving into data, but playing with mathematical formulas. However, despite the importance of beauty in physics, as noted by Sabine Hossenfelder, many beautiful theories have proven to be incorrect, and relying solely on beauty is not the best strategy. It's important to understand that individual elements of string theory, such as supersymmetry, contribute to physics. Although there is no proof yet of the existence of supersymmetry, it has been shown to be necessary for eliminating flaws in quantum theory, mutually compensating bosons and fermions, and eradicating the divergences plaguing quantum gravity theory. Not every beautiful theory turns out to be true, but all existing fundamental physical theories possess inherent beauty and symmetry. The primary issue with string theory is its untestability. The energy of gravitons, known as Planck energy, exceeds the capabilities of the Large Hadron Collider by a quadrillion times. In other words, to test string theory, we would need to build a particle accelerator, well, just about the size of a galaxy. Each solution in string theory represents a separate universe, and there appears to be an infinite number of them. To directly test the theory, we would need to recreate new universes in the laboratory. Therefore, only a higher power of God would be able to test the theory directly, as it is based on universes, not atoms or molecules. All this leads to the thought that string theory doesn't meet the basic requirement of any scientific theory, testability. However, its proponents do not see this as a problem. Typically, science relies on indirect research methods, such as studying the echoes from the Sun, from the Big Bang, and so on. We are looking for the echoes of the 10th and 11th dimensions, believing that evidence of string theory is all around us. We need to listen to its echo, rather than trying to observe it directly. One such signal from hyperspace could be the existence of dark matter. It was previously assumed that the universe mainly consists of atoms. However, it was surprising to discover that atoms make up only 4.9% of the universe's mass. The bulk of the universe is beyond our perception, existing in the form of dark matter and dark energy. Dark matter, making up 26.8% of the universe's mass, surrounds galaxies and prevents them from disintegrating, while dark energy, accounting for 68.3% of the universe's mass, is the energy of empty space that pushes galaxies apart and causes them to spread out. Perhaps the proof of the theory of everything is hidden precisely in this invisible universe. Dark matter is strange and invisible, yet it is what holds our Milky Way galaxy together, preventing its stars from flying off in different directions. It has mass but no charge, and it doesn't interact with electromagnetic forces. Therefore, if you try to grab it with your hand, it will pass right through and continue moving down through Earth and emerge on the other side, where gravity will gradually reverse its direction of motion and bring it back to where you are. Dark matter, as incredible as it seems, must exist. Analyzing the rotation of the Milky Way and applying Newton's laws, it becomes clear that there is not enough ordinary mass in the galaxy to counteract the centrifugal force. Galaxies should have become unstable, but they have existed for billions of years. Therefore, either Newton's laws are not applicable to galaxies, or there is some invisible substance maintaining its stability. This reminds me of the discovery of Neptune, whose existence was mathematically deducted to explain the orbital anomalies of Uranus. Today, one of the primary candidates for dark matter is so-called weakly interacting massive particles, like the photino, a supersymmetric partner of the photon. The photino is stable, has mass, is invisible and uncharged, matching the properties of dark matter. It is believed that the Earth moves in a stream of dark matter, which can interact with protons, causing them to decay into elementary particles. There are large detectors filled with liquids like xenon and argon that can detect a collision involving a photino. About 20 research groups worldwide, often located in underground mines to minimize interference from cosmic rays, are searching for dark matter. If a dark matter collision is successfully detected, scientists will begin to study the properties of these particles and compare them with the predicted characteristics of the photino. If experimental data on dark matter matches the predictions of string theory, it would be a compelling proof of the correctness of the path chosen by physicists. Another prospect is to produce photinos in next-generation particle accelerators, whose construction is well underway. In Japan, work is ongoing on the creation of the International Linear Collider. In this device, electrons will collide with positrons. Electrons, unlike protons, are truly elementary particles, making collisions cleaner and requiring less energy. It is expected that at the energy of 250 billion electron volts, such collisions will generate Higgs bosons. In China, the design of key equipment for the circular electron-positron collider with a circumference of 100 kilometers has been successfully completed. This is almost 4 times larger than the Large Hadron Collider. It is expected to be launched in 2030. This collider will allow reaching an energy of 240 billion electron volts. Additionally, there are plans to upgrade it to a proton collider by 2040, which would enable reaching energies of about 100 tele-electron volts. At CERN, a successor to the Large Hadron Collider, named the Future Circular Collider, is being developed, which is expected to reach an energy of 100 trillion electron volts. Its circumference will also be about 100 kilometers. The development of all these accelerators gives hope for the detection of dark matter. If it is discovered, the characteristics of dark matter particles could be compared with the predictions of string theory. By the way, string theory also predicts the possibility of creating miniature black holes in these accelerators. These small black holes would be safe and energetically comparable to elementary particles, not dying stars. There is also hope that scientists will be able to use the greatest particle accelerator of all time for research, the Big Bang itself. Its radiation could provide the key to unraveling the mystery of dark matter and dark energy. The echo or residual glow of the Big Bang is easily detectable, and our satellites record this radiation with high precision. Photographs show that the cosmic microwave background radiation is remarkably smooth, disturbed only by fine ripples. These ripples reflect tiny quantum fluctuations that existed at the moment of the Big Bang. However, there are unexplained spots in the cosmic microwave background. There are theories that these are traces of collisions with other universes. In particular, there is the cold spot, an anomaly in the form of an unusually cold matter in the homogeneous background radiation, which may turn out to be the remnant of a connection or collision of our universe with another parallel universe that occurred at the beginning of time. There are plans to install gravitational wave detectors in space for more accurate measurements. In 1916, Einstein suggested that gravity spreads in waves. But it was only 100 years later that scientists were able to detect gravitational waves originating from the collision of two black holes. Huge detectors in Louisiana and Washington, forming an L shape, capture these waves. For this work, physicists Rainer Weiss, Kip Thorne and Barry Barish received the Nobel Prize in 1917. The Laser Interferometer Space Antenna, or LISA, consists of a system of 3 satellites, creating a network of laser beams between them. This system, located in space, is designed to register even the slightest gravitational fluctuations that occurred at the moment of the Big Bang. The ultimate goal of this program is to record the gravitational waves of the Big Bang and then rewind these data to get an idea of the state of the universe before the Big Bang. This data will be compared with the predictions of different versions of string theory, which could provide information about the multiverse before the Big Bang. More advanced devices than LISA may in the future provide the opportunity to get baby photos of our universe and detect traces of the so-called umbilical cord that connected our universe to the mother universe. The prediction of a multiverse with numerous parallel universes, some of which are even stranger than any Hollywood screenwriter's fantasy, indeed poses problems. String theory offers an infinite number of solutions, each describing a unique theory of gravity. In some of these worlds, the proton is unstable, making the existence of complex matter such as atoms and molecules impossible, leaving only a gas of elementary particles. This questions the reality of these alternative universes and the predictive power of the theory, as it cannot specify which of these universes is real. This problem is not unique to string theory. Newton's or Maxwell's equations also have an infinite number of solutions depending on the initial conditions. Any theory of everything will likely have an infinite number of solutions, depending on the initial conditions. But how do we determine the initial conditions of the entire universe? This means that we have to manually introduce the conditions of the Big Bang from outside. Ideally, the theory itself would have determined the conditions, the temperature, density, and the composition that led to the Big Bang. String theory offers a vast array of options, including our universe, but probably cannot predict only one universe. This is the landscape problem of string theory. Several solutions to this problem have been proposed, but none have gained widespread acceptance. The first is the anthropic principle, which suggests that our universe is unique because it harbors conscious life, capable of reasoning about this issue. In other words, there are many universes, but ours supports the conditions for the development of intelligent life. Perhaps the initial conditions of the Big Bang were tuned to ensure the possibility of life. This is roughly what the hypothesis of universe evolution suggests, according to which, in those universes where intelligent life is possible, it evolves to such a level that it triggers a new Big Bang, creating a universe suitable for life. The anthropic principle also explains why the physical constants of the universe are perfectly suited for life. Theoretical physicist Freeman Dyson noted that the universe seems to have known that we were to appear in it. If nuclear interactions were weaker, the sun would have not ignited at all, and if stronger, the sun would have burned out billions of years ago. Gravity is also tuned to create conditions for the formation of stars and planets, necessary for life. It seems as if the universe is a lottery, and we have won the jackpot. However, according to the multiverse theory, this means that there are many dead universes where life is impossible. Thus, the anthropic principle might single out our universe from many others in the multiverse landscape, thanks to the presence of intelligent life. Michio Kaku has been studying string theory for over 50 years and believes it has not yet been formulated in its final form, so it's premature to compare it with the observable universe. It's evolving in an unusual way, constantly uncovering new mathematics and concepts. In the last 50 years, there had been 3 major revolutions in understanding the theory. However, the final principles of the theory are yet to be determined. Only then will it be possible to compare it with experimental data. Michio compares the study of string theory to searching for treasures in the Egyptian desert. Imagine stumbling upon a small stone protruding from the sand, which turns out to be the tip of a huge pyramid. After extensive excavations, you discover amazing rooms and artworks in the pyramid. Making your way through numerous levels, you approach the last door, which could reveal the secret of the pyramid builders. He believes that in studying string theory, we have not yet reached the deepest level, as each analysis of the theory reveals new mathematical aspects. String theory is expressed through string field theory by one short equation, but in 10 dimensions it already requires 5 such equations. While string theory can be expressed through field theory, this is not yet possible for M theory. However, there is hope that in the future, physicists will find a single equation expressing M theory. The membranes of M theory, vibrating in different ways, are difficult to describe within the framework of field theory. As a result, M theory includes many different equations, but they all describe the same theory. Writing M theory as a field theory will allow it to be derived from a single equation. Perhaps evidence for string theory will be found not in huge particle accelerators, but when someone formulates its final mathematical form. We might not need experimental proofs. If the theory can derive the mass of quarks and other elementary particles from fundamental principles, it will be convincing proof of its correctness. In the standard model, about 20 parameters are introduced manually. If string theory can accurately calculate these fundamental constants, it would be a historic achievement. Deriving known parameters of the universe from a single equation would confirm its correctness. Several approaches exist to solve the landscape problem. One suggests that many universes are unstable and eventually collapse into our known universe. The vacuum is not seen as empty space, but as a place where tiny universes constantly appear and disappear, like bubbles in foam. Stephen Hawking described this as space-time foam. Most of these microscopic universes are unstable and disappear almost instantly. When the final formulation of the theory is found, it will likely show that most alternative universes live only for a Planck time, about 10 to the power of minus 43 seconds. In comparison, the age of our universe, 13.8 billion years, is immense. Thus, our universe may stand out among an infinite number of other universes. If the final equation is too complex for manual solution, computers might be used. For instance, in quark theory, computers were used to approximate spacetime as a lattice, allowing the simulation of Yang-Mills interaction, acting like a glue binding quarks into a proton. Using a similar method, we could impose M theory on a lattice and perform calculations. In such a scenario, the output of the supercomputer would show our universe. Evidence for string theory might be found in a new generation of particle accelerators, particle detector in a mine, or gravitational wave detector in space. If not, perhaps someone will find the final mathematical formulation of the theory of everything, which can be then compared with experimental data. Michio Kaku is confident that over time we will find the theory of everything. But the next question arises: where did string theory come from? If there is a grand design, did it have a creator? And if so, does the universe have a purpose and meaning? We've seen how mastering the 4 fundamental forces of nature has led not only to unraveling many of its mysteries, but also to scientific and technological revolutions that have changed the course of civilization. Newton, by formulating the laws of motion and gravity, initiated the Industrial Revolution. Faraday and Maxwell's discovery of the unity of electricity and magnetism sparked the Electrical Revolution. The works of Einstein and quantum physicists on the probabilistic and relativistic nature of reality have become the basis of modern high technology. We are now approaching a theory of everything that unites all 4 fundamental interactions. Let's assume we have developed such a theory, but how will it affect our lives, thinking, and perception of the universe? In everyday life, the impact will likely be limited. Each solution of the theory of everything represents a separate universe, and the energy scale of the theory corresponds to Planck energy, many times exceeding the energy of the Large Hadron Collider. This concerns the mysteries of the birth of the universe and black holes, not our daily life. However, the philosophical aspects of this theory, addressing questions about time, the origin of the world, and the emergence of the universe, may touch our lives. The great zoologist Thomas Huxley in 1863 emphasized the importance of understanding humans' place in nature and connection to the cosmos. Einstein's secretary Helen Dukas once mentioned that Einstein was swarmed with letters asking him to explain the meaning of life and whether he believed in God. He said he was unable to answer all these questions about the meaning of the universe. Einstein's letter about God was sold for nearly $3 million, indicating deep interest in this topic. In his letters, Einstein pondered the meaning of life and God, noting the difference between a personal God and Spinoza's God, embodying order in the universe. He believed in God as a symbol of order and regularity, characterizing the beauty and simplicity of the universe. Einstein compared himself to a child in a vast library, trying to unravel the mysteries of the universe. He left open the question of who created these books and whether there is a librarian of the universe, which leads to questions about the origin of physical laws and whether the universe has a purpose. Moreover, Einstein was troubled by another question: did God have a choice in creating the universe? The questions about the existence of God become less certain when we try to apply logic to prove or disprove them. For example, Stephen Hawking did not believe in God, arguing that the Big Bang happened in an instant, so there was simply no time for God to create the universe as we see it. In Einstein's original theory, the universe expanded almost instantly. In the context of the multiverse, it is just one of many bubbles that constantly emerge and disappear. This implies that time could have existed before our universe. The multiverse might be eternal, leaving the question of God's existence unanswered. On the other hand, theologians have sought their answers for centuries. Saint Thomas Aquinas in the 13th century attempted to prove God's existence through logic. He proposed 5 famous proofs of God's existence. These proofs are interesting because even today they raise profound questions related to the theory of everything. 2 of them duplicate the rest, so the proofs can be condensed into these 3 points. 1. The cosmological proof. Bodies and objects move because something pushes them, meaning that something initiates their motion. But what was the first mover that started the universe? It must have been God. 2. The teleological proof. Everywhere around us we see objects of immense complexity, but every construction requires a constructor. The first constructor was God. And 3. The ontological proof. God is the most perfect being conceivable. Yet one can imagine that God does not exist. But if God did not exist, he could not be perfect. Therefore, he exists. Kant in the 19th century found a flaw in the ontological proof, separating perfection and existence as different categories. Nevertheless, the other proofs require reinterpretation in light of modern science and the theory of everything. The teleological proof can be contested from the standpoint of evolution, which explains the complexity of life through natural selection. The cosmological proof becomes more complex with the introduction of the multiverse concept. Although the multiverse can explain the origin of the Big Bang, it leads to the question of the origin of the multiverse itself, and then the origin of the theory of everything. Physicists cannot explain the origin of physical laws, leaving the question of the first mover open. Symmetry, likely to be key in the theory of everything, comes from deep mathematical truth. But where does mathematics itself come from? The universe is a remarkably beautiful, organized and simple place. And yet all non-physical laws of the universe can be written on one sheet of paper. On this sheet, there is definitely room for Einstein's theory of relativity and the Standard Model, which, despite its complexity, describes almost everything in our universe, from microparticles to galaxies. Given the limited scope of this piece of paper, it's hard not to think that everything was planned in advance, that in the elegance of the universe we can see the hand of some cosmic designer. For Michio Kaku, this is the strongest argument for the existence of God. Nevertheless, science is based on verifiable and falsifiable facts. Unlike other fields such as literary studies, where things get more complicated over time, physics strives for simplicity and logic, relying on a small number of equations. But this doesn't mean that nothing meaningful exists outside of science. For example, negative claims cannot be disproven. If we try to prove the absence of dragons, there will always be a chance of their existence in unexplored places. Eliezer Yudkowsky, a renowned artificial intelligence researcher and advocate for rationality, emphasizes the importance of scientific falsifiability. The strength of a theory is not what it allows, but what it prohibits. If you can come up with an equally persuasive explanation for any outcome, then you have zero knowledge. Thus, questions about the existence of God and the meaning of the universe will remain unsolvable, as they are unverifiable and beyond the scope of conventional science. Considering the necessity to explain the prime mover raised by Thomas Aquinas, one is eager to understand where does the theory of everything itself come from. Michio Kaku believes it exists because it's the only mathematically consistent theory. All other theories contain contradictions. Moreover, during the development of the theory, problems arise, such as infinite divergences or anomalies, which disrupt symmetry. Probably there is only one theory free from these constraints. Our universe cannot exist in 15 dimensions, as this would lead to contradictions. String theory confirms this, as quantum corrections often contain a multiplier, d10 or d11, indicating that the only consistent universe exists in 10 or 11 dimensions. This might be the answer to Einstein's question, did God have a choice, in the search for a theory of everything. There is only one equation capable of accurately describing our universe, as all other equations are mathematically contradictory. It may have an infinite number of solutions, but the equation itself is unique. This brings us to another intriguing question. Why does something exist rather than absolute nothing? In quantum physics, absolute nothingness doesn't exist. As we know, black holes are not completely black and gradually evaporate. Similarly, in quantum theory, the minimum energy is not zero. Even in a state of minimal energy, atoms are still subject to quantum fluctuations, as the complete absence of energy would violate Heisenberg's uncertainty principle. So where did the Big Bang come from? Michio Kaku writes, most likely it was a quantum fluctuation in nothingness. Even nothingness or pure vacuum continuously froth with matter and antimatter particles that emerge in pairs in the vacuum and then disappear back into it. It was in this way that something came from nothing. Hawking referred to this phenomenon as space-time foam, an infinite number of microscopic universes emerging from the vacuum and disappearing back into it. These universes are invisible, as each is smaller than an atom. But sometimes one of these universes doesn't dissolve back into the vacuum but begins to expand, leading to the inflationary process and the birth of a new universe. Thus, our universe came not out of nothing but out of quantum fluctuations of the original nothingness. Unlike many other universes, it managed to persist and continue expanding. Two great religions, Christianity and Buddhism, have completely different views on the existence of a creator. Christianity believes that God created the world at a specific point in time. George Lemaitre, a Catholic theologian and physicist, believes that Einstein's Big Bang theory did not contradict the Bible. In Buddhism, on the contrary, there is no concept of God, and it is believed that the universe has no beginning or end, only eternal nirvana. How can these opposing views be reconciled? The universe either had a beginning or it did not. There are no intermediate options. Surprisingly, the multiverse theory opens a new perspective on this contradiction. Perhaps our universe did have a beginning, as described in the Bible, but according to the inflationary theory, Big Bangs occur constantly, giving birth to many bubble universes. These universes may expand in a more extensive space, akin to nirvana in hyperspace. Thus, our universe has its beginning as a three-dimensional bubble floating in a more extensive 11-dimensional nirvana, where other universes are constantly born. Interestingly, the concept of the multiverse allows for the integration of Christian creationist mythology with Buddhist nirvana into a unified theory that aligns with non-physical laws. Michio Kaku writes, I'm convinced we create our own meaning in the universe. It's too easy and simple to look up to some guru who has descended from the mountain tops and brought us the meaning of the universe. To understand and appreciate the meaning of life, effort is necessary. If it is presented to us ready-made, the idea of meaning loses its value. The meaning of life available for free would lose its significance. Everything that has meaning is obtained through struggle and sacrifice and is worth fighting for. However, if the universe is ultimately doomed to die, it's hard to assert that it has any meaning. Interestingly, physics has indeed pronounced a death sentence on the universe. All debates about the meaning and purpose of the universe may seem pointless in light of its inevitable end in the Big Freeze. According to the second law of thermodynamics, everything in a closed system will eventually break down and disappear. Everything will ultimately die along with the universe itself. But perhaps the combination of quantum theory and relativity theory will offer a way for the universe to survive. The second law of thermodynamics applies to a closed system, but in an open system, where energy can come from outside. This rule can be circumvented. For example, an air conditioner receiving energy from outside cools the air, and life on Earth, thanks to the sun's energy, transforms food into new life. Another example is wormholes. They may offer a way to leave our universe. It appears closed, but perhaps in the future we can use our scientific knowledge to create a tunnel through space and time and stabilize it using negative energy and the Casimir quantum effect. Our descendants may reach Planck energy and use advanced technologies to transition to another warmer universe. Thus, quantum gravity may become not just a mental exercise in 11-dimensional space-time, but also a cosmic lifesaver, allowing intelligent life to overcome the second law of thermodynamics and relocate to a more favorable universe. Therefore, the theory of everything is more than just a beautiful mathematical theory. In the end, it might be our only salvation. As Stephen Hawking wrote, if we discover a complete theory, it should be understandable in broad principle by everyone, not just a few scientists. Then we all, philosophers, scientists, and just ordinary people, will be able to take part in the discussion of why we and the universe exist. The answer to this question would be the ultimate triumph of human reason, for then we would know the mind of God. Thank you for watching. I hope such a complex topic became clearer to you, even just a little bit. It takes a lot of time to make these videos. The first one took almost 2 months. If you liked the video, please subscribe to the channel to receive notifications of new videos. Also, you can check out my Patreon page, where I have published a selection of books about string theory and movies about the multiverse. Thank you for support. See you soon.